Hello, welcome back. This is Calculus by Dr. Oz. Today we are given four alternating series, and we're going to determine the convergence or divergence behavior of the given series. We have a very special test only applicable for alternating series. It's called alternating series test. So we're going to try to see if we can apply the test for the given infinite series. So we have four of those series. We have a long way to go. Why don't we start?
All right, let's start. So before we hit the road, why don't we read out the alternating series test carefully and how we can apply or what the conditions are here. So let's say like we have a positive an to start with, The alternating series minus 1 to the n an or minus 1 to the n plus 1 an, doesn't matter which one you deal with. The name, by the way, alternating comes from the sign of the terms, because if you open that up, so if you expand this out, for n equals 1, it's going to be negative a1. For n equals 2, it's plus a2, minus a3, plus a4, and on and on and on. See that the sign is alternating all the way. But as long as an is positive, as you see, based on the very first sentence, okay? So these series converge if the two conditions hold true. One is that the limit of the general term has to be 0. Okay, that's one limit. This is Calc 1, obviously, checking the limits of sequences. And the second one is like an plus 1 is less than or equal to an for all n. That means an should be a decreasing sequence, okay, or non-increasing sequence. How about that? Okay, so in the first condition, we're going to prove that the limit is 0. In the second one, we're going to prove that an decreases for all n. Okay, so then we can go back and just say that the alternating series converges. Okay, so let's see what is the first series. So the first series is like minus 1 to the n divided by n squared plus 5. Okay, so let's grab an, because an is the part which is not alternating. So alternating part of the series is this one, okay? Because every time when you change n from odd to even or even to odd number, right? So that becomes plus or minus. So the non-alternating part is called an. So n squared plus 5. All I'm going to do is just to check two conditions here. Limit of n over n squared plus 5. Okay? Well, the top is infinity, n is going to infinity, and the bottom as well is infinity, so it's an indeterminate form. There you go. You can use the L'Hopital's rule. So I'm going to take the derivative of the top, that's 1, and the derivative of the bottom. Okay? So now I can pass the limit. That's 1 over infinity, so that takes me to 0. There we go. I put a check mark here that the first condition is met. Okay? The second condition is to prove that an is decreasing. There are alternate ways to do that. You can just look at this inequality to prove, which is essentially the same as proving an plus 1 over an is less than 1. Okay, proving this is exactly the same as this one. Or I can treat an as a function, and I can take the first derivative of that, and if the first derivative is less than 0 for all n, then I'm good to go. Then f is decreasing. So I'm going to look at, in other words, an equals fn. So in this case, f of x equals x over x squared plus 5. Okay. All it boils down to taking the derivative of that. Why don't we find that? So f prime. Well, let me just write f first again. So here we go. F is x over x squared plus 5. Okay. And then f prime is the application of the quotient rule. Okay, the derivative of the top is 1 times the bottom, minus the derivative, keep the first, keep the top, and take the derivative of the bottom. Okay. And then you divide by x squared plus 5. So let's just simplify the top. You take the square here, by the way. because of the quotient rule, right? So 5 minus x squared divided by x squared plus 5 squared. Okay. Let's check. So here, an plus 1 over an plus 1 is less or equal to an, so f prime should be negative, right? So let's check if it's negative. If you look at the series here, series starts from n equals 1, so we got to be careful, because then that if x is 1, this is not good. If x equals 2, because this is 5 minus 4, if x equals 2, then that takes you to positive f prime. So as long as x is greater than or equal to 3, then this is less than 0. Okay, this essentially means that I'm considering the infinite series starting from 3, which is okay. F is a decreasing function. F is a decreasing function. So let's say for x is greater than or equal to 3, f is decreasing. Okay, fine. So I can go back here that f is decreasing, right? F is decreasing, or let's put it this way: an is decreasing, because if f is decreasing, an is decreasing for n greater than or equal to 3. So that means that these two conditions met. So the alternating series, okay, n squared plus 5, where n starts from 3 all the way to infinity, is convergent. So this sum is convergent. So you have infinitely many terms adding up to a finite number, and you have 2 more terms coming from here for n equals 1 and n equals 2. Well, adding these 2 terms to this infinite sum here is not going to change the finiteness of the sum, convergency of the sum. So the sum is going to be convergent. So don't get fooled with the statement here saying that this is true for all n. But if you start n from 3, like in the integral test, right? Sometimes we pick the lower limit of the integral to be 3, 4, depending on the conditions of the integral test, right? So it's the same deal here. So if you have to start n from 3, that's fine, because you're just excluding a few terms like n equals 1 and n equals 2 cases, right? So we proved here that this infinite series is convergent. So is this one, right? So is this one, because the difference between this series here, and this one is just essentially you're just missing 2 terms in the first one. Here I have the visual for the partial sums and how I applied the alternating series test here. So as you see that an plus 1 minus an is negative whenever n is greater than or equal to 2. And the limit is always 0, as you see. And the sum, as you can watch from the animation here, that it fluctuates back and forth between minus and plus values since this is an alternating series. But eventually it converges, and it converges to this blue dashed line, and that's somewhere close to like negative 0.05. Okay, so this is sort of like how you visualize the sum of alternating series.